Welcome everyone for today's FAIRWork webinar with the title Knowledge Base, Digital Twin, Data Reliability and Interoperability. So what my colleague from Jotne, Rishank, will tell you today is about how we use their knowledge base, which was created by Jotne in FAIRWork to save data, create digital twins, exchange data, and as a basis for all our AI services. And without further ado, I want to hand over to Rishank. Thank you very much, and you can start with the content of this webinar. Thank you.
Thank you, Christian, and welcome everyone, and good morning to all. I am your presenter, Rishank, and today I would like to take you to this slide set for next 20 minutes about FAIRWork knowledge base, which is used in this project. And before that, I would like to give a short intro on the FAIRWork project itself. FAIRWork is an EU Horizon research funded project, and our primary objective in this project is to leverage AI to provide decision support in especially on manufacturing sector for providing decision support to production managers or production line owners, wherein by bringing all the required stakeholders like the operators, the machines, the robots, where we would like to get their preferences and their capabilities into this decision making scenario. And by this we would enable the democratization where everyone have a say in the decision output that has been provided by these AI services. Given this context, we will going to the next slide, where Yotna is one of the key project partner in this project, where we are offering our standard based data solution, where we can store all the relevant data. And Yotna has long-standing experience in developing standard based products like Express Data Manager, which is based on ISO 10303. And this standard based database itself is a kind of core component of our company, where we are using this database and build some applications for simulation data management called OpenSimDM, and then for product data lifecycle management, which is EDM 2PLM application that has been used in this project. And then we have building information management that is called eBeam. And all these products or applications are based on our standard based database manager. And we have several customers like Lockheed and Airbus, which uses these databases for exchanging their engineering data. With this information, I would just go through some of the points. As Christian has pointed, we would like to cover some of the aspects. We should first establish what is the definition of a digital twin, and then how we can create these digital twins in one of our standard-based data solution. And then I would like to also cover some aspects how by storing this data in a standard-based repository, you will get some of the aspects of reliability, which is crucial for AI applications where data is important and it should be reliable and trustworthy. And then we also see how this repository enables interoperability, that is where different components that have been used in our FAIRWork architecture can interact with this knowledge base and retrieve data. And then we will have some time for question and answers. With this, I will try to explain or give a short intro on a digital twin definition, as there are hundreds of definitions available to say what is a digital twin. So here is one of the definition from the standard itself. A digital twin is a virtual replica of a physical entity, and the digital twin and physical entity can be bridged together by having a continuous stream of data. It can be a single direction or bidirectional, and when it's a bidirectional, where the target entity itself has been changed its behavior or its state because of the decision that has been made from the digital entity. And this digital entity or virtual replica can be used for simulations or for real-time analytics and prediction using AI, or it can also use it for simulation data management, where users can get a complete overview of an physical asset or a process or a machine in a plant layout, and they can get overview of the systems sitting somewhere in a different location, geolocated locations. So with this definition, we will see how we can create digital twins in our FAIRWork project for some of our use cases. Before that, as I told you that in this project, we are using the DAI-DSS knowledge base, which is based upon this standard 10303 repository. This is the primary storage solution that is being utilized in our FAIRWork project. In this standard based storage solution where we can store all the relevant data that is needed for within this FAIRWork project for providing decision supports, as AI algorithms itself need some data to make decisions. So we use this repository for providing decisions. And the capability of this data storage is we can create digital twin or digital shadow representation of a physical entity, and then we can also store integrate IoT data within this repository. And then the application itself provides a web client which can be used to manipulate or create new data instances in this repository. And the core of this application or the backbone of the system is the Express Data Manager, which is a standard-based data repository, and it uses one of the application protocol of ISO 10303, that is AP239, which is a product lifecycle component system. And this is the primary data dictionary or the schema that has been utilized in our database, and based upon this we will build required projects and then configure required information into these projects. With this information, I would like to introduce our end users or the clients that are required the AI decision support in their manufacturing environments. One of them is Flex, which is an robotic manufacturing company. They use these automated robots to produce different components, from PCB components to several components related to automobiles like electronics and some other components. Similarly, CRF is one of our other end user, where they have a production line to produce assembly parts of car. And then we have these following use case scenarios based on each of our end user. And in CRF, we have some use cases like workload balance and handling delay of materials, inventory management, and then also ensuring that the quality of products remains consistent according to production requirements. These are the three scenarios in CRF which we are focusing, and utilizing different or various AI services to tackle these use case scenarios. With this information, I would like to go more in depth into the CRF use case. That is on the slide on the right hand side, you see an image which is a production plant layout of the CRF, which has a series of sections like UT1, UT4, and UT8. These are, we can say, an assembly units or sections of the plant, and then we have each section has a series of lines which are numbered. As you can see, in UT1 you have line 5, 7, 9. Each line consists of a series of dyeing or stamping machines. From one end, a operator will take a raw material or a sheet metal, and then he will place into these dyeing machines, and then at the end of this line you will get a finished product or required component that has been went to these molds. And this is the use case scenario where the CRF would like to allocate operators on these lines based on their previous experience, and then also their training capabilities, and then difficulty to handle these geometries, and also taking in consideration also the production requirements and other scenarios. So to represent this use case scenario or the data required for supporting this use case scenario with the AI, we have created appropriate digital twin representations of this production plant layout. And in this slide, what you see on your left hand side of the screen is a connection graph or the data entity representations of the required plant layout that has been created in the knowledge base or the EDM 2PLM application, where we can see that you have UT1, and UT1 has several uh, pointers that are moving out, that line 11, line 7, and line 9. These are different lines in these UT sections, and each line has a geometry. Each line can produce certain set of geometries that are already available in this production planning. So we would like to capture this information that on a given line, what are the geometries that can be produced, and how many operators are required to produce each geometry, and also what are the training capabilities that each operator has to produce a given geometry on a given line. These are all the required information that we have identified to support this use case scenario. Apart from that, to bring the operator say into the decision making scenario in this AI services, we have also included operator resilience as a factor, and operator preferences as also another factor which will influence the decision output produced by these AI services. And it is also important to capture this information in our system, and we have created required placeholders like operators preference information and suitability information, other related information to store in the knowledge base. With this, now I would like to also address few points that has the data reliability, as AI services need data, and also the end user or the partner who is using this AI services also should be uh, make aware, or he or she need to know the data that has been used in this AI services is reliable and trustworthy, because that is important, as the services, the decision output obtained from these services will impact the persons who are working on the line. And so it is important for the operators as well to know that data that has been used is not biased, and also it's safe and secured, and if needed they can also look into this information. To enable this, we can see that how the standard based repository can address some of these data reliability aspects. And the data reliability itself is defined as a dependability or trustworthiness of data that can be used to make decisions. And at least in this FAIRWork project, we have identified few attributes. What is defined as a reliable data, that is it should be accurate enough. That means it should capture all the values or the events that has been happened or will happen in the plant layout, and then it should be consistent. That is, if we exchange this information or export this information to different system, it should withhold the true representation of the data, and then also it should show the same data until unless it is not modified by users. Similarly, it should have a complete data. What does it mean is, we should in this use case scenario where we would like to allocate workers to the lines, we should have all the relevant data that needed to be provided, all the data for the AI services, so that they will not have any missing values or corrupted data or missing information, so that the algorithm works as it should be. And the timeliness aspect is that it a capability to access the data at the given point of time, and then also modify data if needed, and also retrieve this data from the system and then utilize it for further processing. And now we will see how these four attributes has been covered with the help of a standard based repository. So as I told you that first attribute itself is data accuracy, and because we use ISO 10303 application protocol 239, the 239 itself consists of entities in a schema that provides a standard representation of a product or a machine or a operator by using a template called breakdown templates. And these templates are already available in this schema, so that the definition or the meaning of the information will be always same across different systems. And then apart from this standard based representation, it also provides a ontology we call them as reference data library. With this ontology, what we can do is we can configure required properties and attributes or classes that will define a digital twin entity. Let's say you have a machine and it has some properties like its RPM, speed, RPM, and then torque, and then its manufacturer. If you want to capture this information, we can leverage this reference data library and create these properties, and these properties will be represented in standard manner. On the screen, you see here some of the examples of these standard based ontologies that are already available in this standard based representation. That you can have some classes like future and part contact feature, or occurrences, and part as well. So these are some kind of standard ontologies that are readily available for usage. If not, we can bring our own domain specific ontologies into this system, and we will see how to do that in the next slide. This is the slide which covers the data consistency and data completeness. And you can see the definition of consistency is that we should have the information of a product or an entity available across its life cycle stages. In this case, if we consider it as a manufacturing domain, then it from the design phase to manufacturing and operation and maintenance, all the information about this particular individual entity should be covered and captured and stored into the system. That itself is a consistent, because we use standard based representation, so the semantic meaning will be hold true during all these life cycle stages. Apart from that, as I told you, the standard also provides flexibility to bring your own ontologies into system. That is what we call user-defined RDLs. And on the right-hand side of your screen, you can see a snippet of a geometric info. That is a classification that is specific to CRF use case scenario, where a geometry have certain properties like its design number, and typo is a container that will carry this geometry, and then part is the part number, and then PZ is the number of pieces that this part can be produced or produced on the line. So such kind of domain specific classification types can be incorporated into this standard based repository because of this extensive usage of the reference data library. Apart from that, we can also exchange this information through various systems, as it is a standard based repository. One of the exchange format we call is a step standard or step file format, and this file format can have different protocols, like this is heavily used in CAD models. If you use CATIA or other design modeling tools, there is one of the export format is a step file format, that is AP242 domain model or MIM formats, and we also have other exchange format called X. So once you have information available in one specific format, we can exchange or convert this information into these different formats and use this information in those other systems which are capable to support this exchange format. And apart from this, I want to also give an instantiation example of bringing your own RDL or ontologies into the system. Here is such an example where, as I told you earlier, that each geometry will have certain properties. We have configured these properties in our standard-based repository, and here on the right-hand side of your screen, you see the highlighted yellow color boundary box where the properties has been instantiated with some property values, which gives required values for each geometry. On the line 17, we have several geometries, and each geometry has this classification type, and we need to capture all of these properties. And here is an example of such the information available in the knowledge base. Based on this information, other components involved in our FAIRWork architecture can extract this information, and they have same semantic meaning. So if the output from this extraction is also the same, and you get the properties and the information, based on this you can provide decision support or decisions that can be understood by the end users, because the attributes remains the same or the domain context remains the same during entire this process. And one more thing we have here is the reliability aspect, is that we should able to track the information that has been changed. That is also an aspect of change management. So the standard based repository offers versioning, so you can version the change in product breakdown structure. In our system, we store everything as a hierarchical breakdown structure with relationships. So it is important that we need to know that what has been changed in this product structure, so that we know from version 1 to version 20 what has been changed, and who made this update, and when this has been updated, so that everyone has a say. Everyone, the data stored in the system is transparent, so everyone know what has been changed and why it has been changed. Apart from that, we will also have a dedicated entity based change log. Like if you have a represented a machine as a digital twin entity, so we can also see the change in property values. Let's say you have changed a property from a machine that it's manufacturing to some XYZ to ABC. You can capture this change in these property values and see what has been changed, and you can always trace back to these values, or if there is a decision made on certain value and there is a change in decision because there is a change in different value, then you can always compare why this has been happened. So you can kind of have this tracking of decisions as well, and also tracking of information or change management. Apart from this, we offer standard-based REST APIs from the system itself. So it's not always you need to enter into the graphical user interface to retrieve the data, but you can also use REST APIs to extract this information. Here on the right-hand side of your screen, you see some of the examples of these API methods. It only shows post method as of now, but there are get methods as well to retrieve information. On the left hand side, you can see there is one more a version comparison. It's just to give an example of change in product breakdown structure. Here I am showing difference between version N and version 8. where there has been significant change, that some elements has been added, some has been removed, and you can see the person who has changed this information when it has changed with the timestamp and other information. So this is also, this enables that the data is transparent and can everyone will have a overview of what has been changed over the period of time. With this REST API methods, what we can achieve is interoperability. In the FAIRWork architecture or the framework, we have different components. Each component is an isolated environment, or we call it as microservice based approach, where each individual application on its own isolated environment, and we will cover this in following slides. But here I would like to give an example of a data extraction from the knowledge base. Here you can see there is an object attribute or entity called operator presence. What we will store here is the number of operators that has present on a given day. And we can see on the right hand side that the REST API JSON response of this information that has been extracted from this knowledge base. And this is how we can extract the information, and the AI services in our FAIRWork ecosystem can use this several of the data retrieved from the knowledge base to provide recommendation support. And here is the overview of high-level architecture components that has been involved in our FAIRWork ecosystem. The first component itself is a configurator. This is the starting point of our decision making scenario, decision support system, where we identify the processes, the use cases, and define the decision process model from starting point to end point. Who are the try to capture who are the involved stakeholders, what are the decision aspects that are required, and what is the data that is needed to make a certain decision. Based on this information, we have captured, as you see in the CRF use case scenario, we have captured this production plant layout, and we identified that we need to enable this worker allocation to lines. We need to know the number of operators that are present in the line, and then we need to know their training capabilities, and then we also need to know the production order requirements on a given day, and we also need to know the line properties, like what are the geometries that can be produced on this line, how many operators need to be allocated on this line to produce this geometry, and then also what is the deadline. With all this information, we have algorithms that make trade-off between various parameters, and one of those in this process, we also brought some operator preferences as an attribute, where operator can give his preference, saying that I need to work on this particular geometry on this day because he want to change his routine. So these kind of preferences, as well as their resilience, like measuring their psychological strain working on a given environment, is also measured and captured into the system. And with this information available in the knowledge base, then we can use corresponding AI services. And here is such process which I would like to say how various components can interact with the knowledge base. The configurator itself will, as I told you, is the starting point, and then based on the information the decision process models has captured, we will create appropriate user interface layouts where users can interact to get a decision support. This is the first aspect, that we configure some graphics layout and provide it to user interface and then we will also have this microservice based approach, where each service can be included, or we can make several services into a workflow based orchestration using Netflix conductor. These series of microservices can be invoked from this workflow, and this orchestrator kind of get all this required information. Apart from this, we can also store decision process models in the knowledge base, and then the user interaction with the FAIRWork ecosystem will start. That first, the user will request for a, let's say for CRF, we want to allocate worker to the lines. There will be appropriate graphic layout for this component. There will be a button or some user interface for invoking a service, get allocate workers to the line. With this input, it will go to this orchestrator. The orchestrator has been configured with series of workflows. These workflows can be like retrieving data from the knowledge base, and then collecting and parsing this data and making it a suitable representation format that is needed for AI service. And this invoke this AI service with this data and get the result back, and do some post processing, and then get it back to the user interface. Here is such interaction. What you see is that user has made a request to orchestrator. The orchestrator will invoke a AI service, and the AI service will retrieve some data from the knowledge base for whatever decision it need to make, and then the knowledge base sends the response back, and then the service will send the response to the orchestrator. And if needed, if we need to enrich this decision with more information, then the orchestrator can request more data from the knowledge base, and then this data is sent back, and the orchestrator will get all these results, parse them, and send it back to user interface. By this, you can see that various components in this system are interacting with the knowledge base with the help of REST APIs, and get the data to end user with the required decision support. With this, I would like to conclude this webinar, and I would like to summarize what we have discussed. That I tried to explain what is a digital twin and how we can create a digital representation of physical entities in this standard-based repository. And having a standard-based repository will cover some of the reliability aspects like accuracy, consistency, and data integrity and interoperability. And we have seen how it has been achieved. And also we have seen how components in the FAIRWork architecture will interact with each other and provide decision support to the end user. With this, I will conclude my presentation and open the floor for question and answer sessions. Thank you.
So thank you very much, Rishan, for this very interesting presentation. And therefore, the question in the audience: are there any questions? Something that should be explained in more detail? Something of interest that should we discuss now? Thank you very much. Then we end the webinar here. So thank you for joining us. We have our next webinar on the 5th of February, where our use case partners will introduce the current status of the evaluation. So the first insight, what they have already evaluated of our prototype, and how they plan to further evaluate it. So if it's interesting, it's on the 5th of February, and you can already register there. And otherwise, then thank you very much for joining. Have a nice day and a nice weekend, and see you soon, hopefully. Thank you. Bye.